Welcome to radar system course. We have seen that earlier delay line canceller, single delay line canceller, and then double delay line canceller that we have seen. The delay line canceller is nothing but it rejects stationary objects, or you can say that it rejects the stationary clutter at a zero frequency. And a delay line canceller is a time domain filter. Even we have seen that a two delay line canceller or a multiple delay line canceller both are useful for the rejecting the stationary clutter at a zero frequency. Now, there are some blind speed occur. So, to avoid that blind speed, we are supposed to use a high frequency radar, or we can use a multiple frequency radar that we have seen. Now, even if we have considered that a multiple issues in a delay line canceller, so that to avoid that a blind speed, we can use instead of a single pulse repetition frequency, we will use a multiple pulse repetition frequency, and that is called the staggered pulse repetition frequency. So, in this case, we consider that for a MTI radar, we are using a multiple frequency signal. Okay, multiple frequency means what? It uses a more than one pulse repetition frequency that will reduces not only the a blind speed, but it also allows a better frequency response of a radar there. Now the generally we can use a line delay line canceller, but again there will be a blind speed. To avoid that blind speed, we can use a multiple pulse repetition frequency. So in a multiple pulse repetition frequency, either we can use a single radar that will providing a multiple PRF, or we can use a two radars with a different frequency there. If you consider that a two radars operating at the same carrier frequency, then they two radars are differ with a pulse repetition frequency. So in that case, a blind speed for a given particular radar occur at a different interval or a different time, even if we are using a two radars say. If we are using a single radar there, that single radar also has a blind speed as compared to the pulse repetition frequency. So instead of that, we can consider that single pulse repetition frequency, we use a multiple pulse repetition frequencies, and then we can use a single radar there. Now, what happen if we consider that there will be a multiple pulse repetition frequency? For example, we consider that a delay line canceller. In a delay line canceller, what will be the response for the delay line canceller? We have seen that this kind of a response we are getting for the delay line canceller. So in this case, we can say that this will be what 1 by T1, 2 by T1, 3 by T1, 4 by T1. And that T1, 1 by T1, okay, that particular repetition time is nothing but what we can say that a pulse repetition frequency. And in this case, we can write it will be of a 1 by T1 there. Now, we can consider that a pulse repetition frequency we are using, if we are using supposed to be a 2 pulse repetition frequencies, so what will happen here? Okay, 2 pulse repetition frequency. So in that case, our response will be what? Okay, so we can consider that there will be a 2 pulse repetition frequency. Okay, this one is about a T1 now. So I supposed to be consider this one is about a T2 now. Okay, all these are a single pulse repetition frequency in there. So that's about a T1 here. But I supposed to be consider that another pulse repetition frequency. So it is supposed to be considered that a time a T2 now. Okay, 1 by T2, 1 by T2 like that. Okay, so 2 by T2, 3 by T2, 4 by T2, 5 by T2 here. Okay, so now in that case, what will be the FP? FP will be what? 1 by a T2. Okay, so here this one is about a T1, is a pulse repetition frequency, and then T2 is again a pulse repetition frequency. Okay, so now if you combine this both T1 and T2, then what will be the response for this composite response of this T1 and T2? So in this case, we can consider that T1 and T2 is to be combined. Okay, so what will happen here? So I is supposed to be consider that what will happen for the T1 and T2. So this one is about 1 by T2. This one we can say that 1 by T1, then 2 by T2, then a 2 by T1. Okay, so likewise. So we are getting the response that is about a 3 by T2, 3 by T1. Okay, so what will happen to the response here? So for initial case, we can say that this one will happen to the T1, and then this will be for the T2. Okay, so likewise, we are getting the a composite response for the T1 by T2 here. Okay, if we consider that T1 by T2. So what happened here for the given particular staggered pulse repetition frequency? So if you consider that a composite response, then in that case what happened? It is not able to cancel the second time echo. Okay, so whatever the second time echo, second time around echoes from the clutter. Okay, you can say that second time around echoes from the clutter, that will not be cancelled here. Okay, because we can consider that the pulse repetition frequency will be a multiple one. So because second time around echoes will occur at the same frequencies from the same range of a pulse, or we can say that we say that we are sending the signal to the given object, given target with a two different pulse repetition frequency signal. Then in that case, for the given particular range, so it will produces a uncancelled residues there. So to avoid this second time around echo from the clutter, okay, because clutter is nothing but a stationary object. So to avoid that second time around clutter echoes, or to avoid that particular, or to remove that second time around clutter echoes, so we can use a constant pulse repetition frequencies, only the solution to remove the second time around clutter there. or we can change every time PRF, okay, pulse repetition frequency every time. Means at each and every time we need to change a pulse repetition frequency, means we send a signal for signal. So the pulse repetition frequency will be different for the different instant there. So at each and every time or at each and every scan period, the pulse repetition frequency will be a different. So this way we can use a staggered pulse repetition frequency. Okay. Then next we'll see that another topic, a range gated Doppler filter. Now we have seen earlier that a Doppler filter that use to pass the specific frequency band Doppler frequency signal, and it will remove the any clutter or any stationary clutter or any noise there. Okay, it will pass or it will allow only the a clutter there. But here what happened? Our target is moving. So in that case, we need to separate out the signal from moving target, as well as we need to separate out the signal from the stationary clutter. So for that purpose, a delay line canceller is used to remove the stationary clutter. But when we are using a delay line canceller, so in that case what happened? So then we will lose the information about the range. Okay, what will be the information we are losing to this information? Okay, so we can say that we have a loss of information regarding the range there, because we know that what will be the time period for round trip time. Okay, and that round trip time from the moving target, that information we are losing there. Again, the signal from the moving target as well as that from a stationary clutter, when it reaches there, so then both the signals are collapsing, so that's why there will be a collapsing loss, and that loss of the range information as well as the loss from this collapsing the signal, that can be eliminated by quantizing the signal in a time, or we can say that quantizing whatever the signal we have received into a small interval in a time there. Okay, so now what we can do here? So now that process of quantizing the signal, okay, in a time, in a small, whatever the quantization occurs in a time with a small interval, that process is called as a range gating. Okay, we use a range gating there after your phase detector. Okay, and that phase detector range gated means what? A quantized time interval signal, small time interval signal that will be provided to the range gator, and that will pass only the small section of the signal. Okay, that signal in a small interval that is supposed to be passed through. Now we can consider here, so output from the phase detector, this one we have a phase detector for what? From this moving target indicator or MTI radar, and that output from this phase detector, that will be given to the different range gate here. You can consider that range gate 1. Similarly, we have a range gate 2 here. Okay. So then we have a range gate 3 here. Okay. So then we have a range gate n. Okay. You can say that range gate n. Okay, this one is about a nth range gate. And then we can consider that output of this one is about a phase detected output. Okay. And then that will be provided to the display, and for the display we use a delay line canceller. Okay. So instead of a delay line canceller, we use a range gated Doppler filter. Okay, range gated Doppler. This one is about a range gated. Then we use another block that is about a boxcar generator. Then we have a band pass filter. Okay. Then we have low pass filter. Then we have a threshold here. This one we can say that boxcar generator. Okay. Then a threshold, and after threshold that will be given to the data processing or a to display there. Okay, whatever the output we are getting, that will be given to the display. Okay, so likewise, so that is to be given to the a display here. Now what happened here? So I missed one more block here. So pass filter, boxcar generator. Okay, and then we have a band pass filter. We have a full wave linear detector. Okay, so this one is about a full wave linear detector, because our signal from this band pass filter, it is about what? This one signal is about a bipolar. That's why we have a full wave linear detector. We are getting the signal, okay, bipolar one. Okay, then we need to convert it into a, what you can say that, a unipolar one. Okay, so that's why we have a full wave linear detector. So it will convert that output into a unipolar. So that signal to be displayed on the display. So display will be of a unipolar one. So that's why we use this one, a full wave detector. Okay, so range gate, then your boxcar generator, band pass filter, full wave detector, linear detector, low pass filter, and a threshold here. Now here we can consider that a process. In this process, we say that output from the phase detector, that is to be quantized, okay, into a small interval there. Okay, so that is about to be quantized in a small interval through this range gate. Okay, so that is about a quantization is to be takes place here. And this process is known as a range gating here, because we are quantizing the time into a small interval. So that process is called as a range gating. And then that particular width of this range gate, that is about a interval, what we can say that that interval is depends upon that what will be the accuracy required, okay, or accuracy desired. So after quantizing, so this is about the quantization takes place here. Then whatever the output from this radar range, that is about through the intervals, that is given to the a boxcar generator there. So this boxcar generator, if you consider that in a MTI radar, there are the multiple range gates we are using. Okay, that multiple range gate that is to be used, and here we have a filter, band pass filter. Here we can see that Bosca generator and a filter. Okay, that used to process the filtering. Okay, that boxcar generator, as well as we have a band pass filter. Both are used for the filtering, or we can say that that will be used to eliminate whichever the harmonics present at the receiver there. That eliminating the harmonics of a pulse repetition frequency. And then this one is about a band pass filter. So it is used to reject the clutter, or you can say that this band pass filter is called as a clutter rejection filter. And this bandwidth of this particular band pass filter is depending upon that what will be the expected clutter spectrum through this for this particular range gate, or for a given particular interval there. Then full wave detector, we know that it is to be converted bipolar signal into a unipolar one, so that we will get the output. Okay, so full, just like it is just like used as a full wave rectifier we have seen earlier. Okay, so we can consider that our output generally it is about a bipolar one. Okay, here we are getting the bipolar one. Because bipolar means what? Your signal will be what? It will be signal positive peak as well as a negative peak. Okay, so like, so okay, upper one and as well as a below one. So our output is to be converted into a display only the unipolar one. So for that purpose, a full wave detector is to be used. Okay. So now, just like only for a conversion of a signal into the unipolar one, there is low pass filter for a given particular filtration filter. We suppose use a low pass filter here, and then there will be a threshold for a given particular level. We consider the threshold, and that much level signal is to be displayed there. Okay, or it can be given to the processor, or it is to be given to the a display there. Now, if you consider here for this range gate here, a small due to the small interval, we consider due to the small interval, it is easily detecting the signal from the stationary, even it will remove the stationary clutter, and for a given particular interval it will not lose the information regarding the range there. Okay, so that's why we can consider this a range gate Doppler filter to be used to get the information regarding the range also. If you consider that, what will be the, okay, so I think we supposed to be considered that all the boxes are there. Okay, so likewise. Okay, so all the boxes are there. Okay, so these are about the all the boxes here. Okay, so I supposed to consider that these are the all the boxes to be there. Okay, so we consider that all the blocks are there here. Okay, and that will be the input. Okay, so these are about to be displayed. So every range gate. Okay, so output from this each and every range gate that is to be given to the a display there. Okay, so now what will be the frequency response characteristics of this MTI radar that will use a range gate Doppler filter? So if you see the frequency response, earlier we have seen that a frequency response is likewise. Okay, just like we can say that this one is about a frequency response. But if you consider that a frequency response of this range gate Doppler radar, so it will be what? For a given particular frequency here, this one is about the response we are getting. Okay, so this one is about the response we are getting. So if you consider here, so this one is about your pulse repetition frequency. That will be 1 by T. This one is about your twice FP. Likewise, we have a thrice FP. Like, okay, so this one is about your pulse repetition frequency. Okay, so this way. So this one is the frequency response characteristics of a MTI radar that will uses a range gate and a filters. So this one is nothing but what a shape, okay, that is to be considered for rejecting a given particular frequency and allow only the given particular frequency. Okay, that is about a shape of your a band pass filter. If you consider here for all these case here, so after phase detector we use this range gate because we convert that signal into a small interval. So if you consider this one in this case, you can say that for this given particular blocks, okay, so if you see that all the blocks to be used to get the information about the range there. So in this case, to design, while designing this range gated Doppler filter, it will be a more complex than this. What will be, we have considered that MTI single delay line canceller. But if you use this range gated Doppler, so we'll get a better performance as compared to the single delay line canceller. So it will remove the stationary clutter, or we can say that it will not lose the information about the range there. But designing will be a complex here. Okay, so that's about a range gate Doppler filter. Now we'll move towards another topic, that is about a digital signal processing in a MTI radar. Okay, so how this signal will be processed? Digital signal processing in a MTI radar. It's just like we have considered that what will happen for the given signal when we are getting the signal from the detector, okay, at a receiver now, okay, and then that signal is to be detected, okay. So generally if you consider that at a receiver we have the a IF amplifier, okay. So then output of that particular IF amplifier is to be split into a two channels, and then that particular two channels consist of one channel have the information related to the phase, that is about, we can say that information about the phase, so that's why in phase channel that will be denoted by I, and the other is about a quadrature channel that will be denoted by the Q. So means what we have, whatever the input from the IF, okay, so after IF at a receiver we have a IF amplifier, so from the IF, okay, so what will be the output of the IF? That IF will be split into what? It will be split into I and Q. Okay, so we can say that it will be split into the I and Q. And that I and Q is to be given. Okay, this is nothing but a output of this I and Q. Okay, that is to be given to the your phase detector. Okay, and then it is to be converted in a digital to analog. It will convert your information and then it will to be displayed there. So we will see that what will happen here for this IF signal. So now we consider that a signal from the IF. This one is about the IF signal. So we can consider that a signal from the IF. Here we have a phase detector. Okay, this one is about a phase detector. Then we have a sample and hold circuit. Okay, for getting the information. So through that we convert the information flow into the unlock to the digital one. Okay, then we supposed to store the information. Okay, so we can say that a digital store we have, or we can say that a digital storage here. Then we have a subtractor. This one is about a subtractor. And then we can consider that a signal that is about I and Q. So we can say that this is about a I, or we can say that in phase channel. Okay, this is about a I or a in phase channel. And then this particular output, we can consider that phase shifting of 90 degree. That's why we can say that pi by 2 here. Here we have a phase detector. Okay, 90-degree phase. Okay, in between the two signals. Then the same sample and hold. Then A to D. Then a digital store. Whatever we can say that information. Digital storage here. Then we have a subtractor. And then that signal, whatever the signal from the subtractor, that will be given to the, this one is about a subtractor here. So we'll get the magnitude. Magnitude of what? I square plus Q square. Just 1 by 2. Then it is to be given to digital to analog converter, and then to display. Okay. Then to display. Okay, so this one is about a digital to analog converter information, magnitude here, and then whatever the digital storage signal, we supposed to provide the input to the subtractor here regarding the A to D information. Okay, so likewise, you can consider that information to the a subtractor here. So from this, what will be the A to D block? Okay, and then subtractor to the whatever the magnitude we are getting. So simple, if you consider that in blocks here, so we have the IF input, that output of the IF. Okay, so we can say that that output of the IF amplifier, that will be split into the two channels. Okay, is the two channels, one for in phase channel and another from a quadrature channel. Okay, so we can say that a Q. Okay, so or we can say that a quadrature channel. Quadrature channel. Okay, so this one is about a quadrature channel. And this particular detector we have, these two detectors here, we can consider that they are a 90-degree out of phase. Okay, so that's why pi by 2 we can consider here. And then this quadrature channel, if you consider here, as well as the I channel, so both are used to eliminate the whatever the effect of the a blind phases here. So generally, if you consider that a channel I and a channel I, these are nothing but the in phase channel. Okay, and a Q channel, that will eliminate whatever the effect from the blind phases there. So we consider there a signal to be passed through the quadrature channel. Okay, and that channel doesn't have any information. Okay, so more because it is about a phases that change, that two signals are about a out of phase. Okay, that is about, we can say that 90-degree out of phase. So that's why a quadrature signal, it doesn't have information. It has the information related to the a phase there. So it doesn't have a significant information. But this particular information that will be useful for the conversion of a signal into digital to analog to display one. Okay, so means we have after that phase detector. So informations we have, that information is to be converted into a digital one. That's why we have used a sample and hold circuit. And then we will get the video. That will be video. Here sample and hold. Your output will be what? Till here. It is about a bipolar one. And that bipolar video is to be converted into the unipolar one. So that's why your signal is to be converted into analog to digital there, and then that signal is to be stored in a digital memory for every pulse repetition period. That's why we consider that a signal is to be stored somewhere, okay, after that A to D. And then once it is stored, that signal, because we have a signal, initial signal and new signal. So that's why it is to be useful for the subtraction, because after pulse repetition frequency we have, so what will be the signal for the next sweep? Okay, what will be the signal for the next sweep? That will be a subtracted here. And then that subtracted signal, okay, both from the subtracted signal here, that will be taking the square root of a subtracted signal here, and then we'll get the here, that is about a combined I and combined Q here. Okay, so that's why we just get this square root of this one, and then after combining, so we'll get the output that is about a unipolar one. Then convert into a digital to analog, that is about data, so we'll get the unipolar output here, and that unipolar signal is to be displayed on the display devices. Okay, so because we consider that a bipolar signal, we convert into to display on the display devices. Display devices is about unipolar display devices. So that's why we need to convert our signal into a unipolar form. So that's why we use a conversion of the signal from the analog to digital as well as a digital to analog here. So this one is about your digital signal processing, or we can say that a MTI signal processor. Okay, this one is about a MTI signal processor. Okay, next we'll see that what will be the MTI signal detector there, and how it will detect that a digital. Okay, how it will detect the moving target there. Okay, so we can say that a moving target signal processor. Okay, so see that a moving target detector, MTD, is a moving target detector signal processor. Okay, this one is about a moving target detector signal processor. So we have considered that earlier. That is about output from that what? IF. IF is to be converted into a split into a two signal. That is about a I and Q. Okay. So that output of that I and Q we have converted earlier into the analog form, then analog to digital converter. Okay. So we have considered that I and Q signal. Initially that I and Q signal we converted into A to D, and after that we have converted into a digital to analog there. And that digital to analog converter, then it is to be in display one. Okay, that is to be used for the display. So now we will consider here in a moving target detector. So how that target is to be detected. Okay, there will be the target present within a particular range. So then that signal is to be detected whether the target is present or not. So that is nothing but a moving target detector. Okay, so now we consider here that input from that I and Q. that is to be given to the a three-phase detector. That is about what we can say that input from that I and Q here. 3 pulse canceller, then a 8 pulse Doppler filter bank, 8 pulse, Doppler filter bank here, then paying here, and checking what will be the magnitude there. Then it is to be given to the threshold, and then we'll get that a hit report. Okay. Then I and Q, we consider that zero velocity filter. Okay. Then we have what will be the magnitude there, because the target is whether it is moving or not. So that's why what will be the velocity of the given particular target. Okay, so that's why. Then whether it will be from the stationary signal, so that's why a clutter map, recursive filter. Then we can consider that a memory map, or you can say that memory clutter map in the given particular region. So what will be the clutter there? Okay, so that's why output from this is to be given to the thresholding, or after magnitude that is again given to the thresholding there, and then that is to be used to display here. So generally what happen here, so we can consider that a zero velocity clutter. Okay, this zero velocity clutter that is used to eliminate whatever the a signal now, because that signal has a 3 pulse canceller and a 8 pulse canceller. Okay, so generally what happen here, this signal is about a 3 pulse canceller, then 8 pulse canceller there. So this particular block here, it will use a zero velocity clutter there, and that will be that particular zero velocity clutter that will be eliminated by this particular blockchain. Okay. So this one, it 3 pulse canceller, so it will eliminate the stationary clutter. Okay, and then we consider that what will be the magnitude of a given particular signal. So that's why we use a threshold, and then instead of hit report, we can say that display. Hit report means what? For a given particular report, for a given particular level, there will be a signal present or not. That will be detected by this moving target detector signal processor. Okay, so this one is about a filter, Doppler filter bank, and that Doppler filter bank here, we consider that a 8 pulse Doppler filter bank here, and that 8 pulse Doppler filter bank will generate given particular Doppler interval to identify or to find out the what will be the moving target here. Okay, so that is about that's what we have seen here for this moving target signal detector. So what will be the different platform we use for the moving target indicator? So generally, moving target indicator is supposed to be our radar is a fixed. That is nothing but a radar is stationary. but our target is moving. But if supposed to be, if that radar is mounted on a ship or a aircraft, then how to detect the motion of the moving target? Okay. So now these are the signals we have seen that till now. We have seen that a radar is stationary. Okay, so we have seen that a radar is about a stationary one. Okay, this is about a radar is stationary. And we have considered that we need to identify that a moving target. That is about the range of the moving target. But if consider that this particular radar, if the radar is moving, then how to identify from this moving radar to this moving target in presence of a clutter? Okay, there may be a cluster, stationary clutter, or there may be a clutter information unknown in not okay, unnecessary information. So in that case, so what will be the Doppler frequency shift occur from the stationary clutter or from the moving target? That is to be identified, because the Doppler frequency shift of the clutter, that will be varies based on this whatever the direction of the given antenna. So we will consider that how to identify a clutter Doppler shift and how to identify that moving platform of this moving target indicator. So with this we stop here. Thank you all of you.